The culmination of electromagnetic theory in the 19th century was the prediction and the experimental verification that waves of electromagnetic fields could travel through space. This achievement opened a whole new world of communication. First, the wireless telegraph, then radio and television, and more recently, cell phones, remote control devices, Wi-Fi, and Bluetooth. Most important was the spectacular prediction that visible light is an electromagnetic wave. The theoretical prediction of electromagnetic waves was the work of the Scottish physicist James Maxwell, who unified in one magnificent theory all the phenomena of electricity and magnetism. The development of electromagnetic theory in the early part of the 19th century by Ørsted, Ampere, and others was not actually done in terms of electric and magnetic fields. The idea of field was introduced somewhat later by Faraday and was not generally used until Maxwell showed that all electric and magnetic phenomena could be described using only 4 equations involving electric and magnetic fields. These equations, known as Maxwell's equations, are the basic equations for all electromagnetism. They are fundamental in the same sense that Newton's 3 laws of motion and the law of universal gravitation are for mechanics. In the sense, they are even more fundamental since they are consistent with the theory of relativity, which we will learn later. Whereas Newton's laws are not, because all of the electromagnetism is contained in this set of 4 equations. Maxwell's equations are considered one of the great triumphs of human intellect. These first 2 equations are Gauss's law for electricity and magnetism. Let me just write that, Gauss's law. And the second one is the Gauss's law for magnetism. The third is the Faraday's law. And finally, the fourth is the Ampere's law as modified by Maxwell. The last term on the right in the last equation is conceived by Maxwell. It's an addition. Well, let's try to notice the symmetry of these equations. The Maxwell's addition to Ampere's law is essential for symmetry, which is also essential for electromagnetic waves to be produced. These equations can be combined to mathematically obtain a wave equation for both the electric and magnetic fields. In empty space where there is no charge and no electric current, the solution to the last 2 equations showed that the speed at which electromagnetic waves travel equals the measured speed of light, and this result led Maxwell to predict that light waves are a form of electromagnetic radiation. From electromagnetic theory, from now on, I'm gonna use EM as electromagnetic, so and call it EM waves or electromagnetic waves. So anyways, from electromagnetic theory, we know that changing electric field in empty space will produce magnetic field. So let me write that for you. So changing changing electric field, I'm going to call it E field, is going to produce in an empty space, will produce a magnetic field. Produces magnetic field, and we name the magnetic field as a B field, which will be also changing, and so it too will produce a changing electric field. So changing and produces changing electric field, and so on. So Maxwell found that the net result of these interacting changing fields was a wave of electric and magnetic fields that can propagate through space. To examine this, let's consider two conducting rods that are served as an antenna. So when the switch is closed, so this is the switch, is closed, the upper rod quickly becomes positively charged because it is connected to, so this becomes positively charged, and the bottom one, lower rod, will be negatively charged, which will cause electric field lines to form. So we will get something like this. So we know electric field lines go from positive to negative. So I'm going to call it E field right here. Of course, on the other side as well. So will be this way. Oh, focus only on one side. While charges are flowing, a current exists. So going this direction up. And magnetic field is therefore produced near the antenna. So the magnetic field going into the page, and that is if you use a right hand rule. And if you didn't take electricity and magnetism, or you don't know much, you just have to trust this. And then on this other side, the electric field lines will come out of the page. Well, now we can ask, how far out do these electric and magnetic fields extend? In the static case, the fields will extend outwards indefinitely far. However, when the switch is closed, the fields quickly appear nearby, but it takes time for them to reach distant point. Both electric and magnetic fields store energy, and this energy cannot be transferred to distant point at infinite speed. Now let's look at the situation where our antenna is connected to an AC generator. At one instant, AC generator will produce a current in the rods going upwards and generating electric fields going from direction from positive to negative this way, and magnetic fields going inward, so be in. In another instant, the current will flow downwards, generating electric and magnetic field of opposite directions. So this time electric field will go from lower upward. So and the magnetic field will be outward. Because the new fields have changed direction, the old lines fold back to connect up to some of the new lines and form closed loops. However, the old fields don't suddenly disappear. They are on their way to distant points. Well, indeed, because changing magnetic fields produce an electric field and changing electric fields produce a magnetic field, this combination of changing magnetic and electric fields moving outward is self-supporting and no longer depends on the antenna. So the fields near the antenna become quite complicated, but we are not really interested in them. We are interested in fields far from antenna, which we will call radiation fields. The field strengths are greatest in the direction perpendicular to the oscillating charges, and they drop to zero along the direction of oscillation, that is above and below the antenna. This would be some kind of electric and magnetic field oscillating and propagating forward in a direction of the arrow. And as I said, the direction that is perpendicular to the antenna will be the strongest. So now, very far from antenna, the wave fronts, which are the field lines, okay, are essentially flat over a very large area and are known as plane waves. So if the source of our voltage varies sinusoidally, then our electric and magnetic fields, or electric and magnetic field strength, will also vary sinusoidally, and it will give us a picture like this. It is important to notice that our electric field and magnetic field are perpendicular to each other. So I can say electric field is perpendicular to magnetic field, and both of them are perpendicular to the speed of the propagation of the wave. So here I have a 3 dimensions, x, y, z, and then the electric field will travel on the x direction. Okay, so imagine this is electric field lines. So strength, actually, electric field strength. And here how the magnetic field will change. So sinusoidal on the zx plane. So and then magnetic field strength will change as this. Obviously my drawing is not the perfect one, but you can see that electric field and a magnetic field are perpendicular to each other, and the wave is propagating to the right on the x-axis. So let's let's write that. So this is the velocity of the wave. Well, on my next video, we will try to examine how the existence of electromagnetic waves follow from Maxwell's equation. Thanks for watching and stay tuned for more.